So let me begin the next topic by a question. This is actually a question that you could have understand or you think you can do it by using just knowledge from week 1. So for example, if I give you 3 factors, but these 3 factors are very nasty, 1, 2, 3, 4, 5, 7, 8, 9, 10, 11, 15, 17, 19, 21, 23, are they linearly independent? If you try to do this by definition, try to do it, it's very painful. But imagine you do like alpha plus beta plus gamma equal to 0, 0, 0, 0. Then I will obtain 5 equation and then 3 unknown, and then I will totally mess up, okay? Because the equation looks very complicated. So you will ask, is there an easier way and a more efficient way to determine whether a bunch of factors are linear independent or not? The answer is yes, okay? So instead of doing by definition, we are going to tell you how to do it. Use Gaussian elimination to do it, okay? Which is much easier. So before I do that, I want to introduce a concept to you that is called the rank of a matrix. So what does rank of a matrix mean? Actually, it means something very simple, but then it sounds very fancy. So look at definition 10.3.1. It says that rank of a matrix is the number of linear independent rows. Okay? So let me give you an example. For example, the rank. So if phi1, phi2, and phi3 are linearly independent, then what do we know? We know that, the rank of the matrix formed by these 3 factors, if we put all these factors as rows, the rank will be 3, okay? You just count how many independent rows are there, because they are linear independent, so 1, 2, 3. So there are 3 of them, okay? So what's interesting is that once you transform this question into a question about matrices, then you can use Gaussian elimination. And the key theorem is theorem 10.3.1. Let me put a star here. What does it say? It says that the rank of a matrix equals to the number of non-zero rows in the row echelon form of A. So basically what you do is you have a matrix here. Suppose initially you don't know the rank, then what you do is to transform this into row echelon form, and then try to look at how many non-zero rows are there in your row echelon form, and that will give you the rank of the matrix. Okay? But the second part is actually kind of obvious. The rank, the number of linear independent rows, is so if phi1, phi2, phi(n) are linear independent, then just now we know that the rank of the matrix is n, okay? But on the other hand, from what we learned last week, we also know that when they're linear independent, then what's the dimension of phi1, phi(n)? What's the dimension of the subspace spanned by these n factors? The dimension is also n. And what we're telling you in this theorem is that these two quantities always equal, okay? The rank of a matrix and the dimension of the subspace spanned by the rows, they are always equal. And then in literature, this space is usually called row space of the matrix, okay? Because this is the subspace spanned by the rows of the matrix. So as I say, algebra, if you do it like in this way, it's very abstract. It's very difficult to digest. It's a lot easier when you look at a concrete example. And that is what we're going to do now. So this example would be a very good way for you to understand the concept of rank. So let me put a star here. So, part A. Find the rank of the matrix. So what's the idea? The idea is, what is rank? Rank is really the number of non-zero in the row echelon form of the matrix, okay? So let us transform this matrix into row echelon form. So I have 1, 2, 3, 4, 5, 6, 7, 8, and then 9, 10, 11, 12. Okay? So let's do the usual thing. So good, this is 1 already, so we don't have to do anything. So 1, 2, 3, 4. And the entries that I want to kill here is the 5 here and the 9 here. How do I do that? Now you should be able to do it quicker. So the first row, multiply by -5, and then add it to the second row. Then we get 0. And then 2 times -5, -10, add 6. That means -4. And then -8, and then -12. Okay? -8, and then -12. So this is what I did, is multiply the first row by -5, and then add it to the second row. And then how about the 9 here? How do I kill that? Then what we're going to do is to multiply the first row by -9 and add it to the third row. Then I get 0, -8, and then -16, and then 4 times -9, -36, add 12, -24. Okay? And then 1, 2, 3, 4. The next entry that I want to kill here is this one here. Well, this one is easy to kill. Basically, what I do is to multiply the second row by -2. Then I get 8 here. 8 plus -8 is 0. So what we're going to do here is multiply the second row by -2 and add it to the third row. So the second row unchanged. And the third row, okay, this times -2, 8, plus -8, 0. But then you realize that, well, it's still everywhere. So 0, 0. Okay? And then you realize that in this case, this is already upper triangular shape, so this is in row echelon form already. Okay? Then what is rank? Rank equals to the number of non-zero in the row echelon form. So we count 1, 2. Okay, this is 0, so you don't count this. So 1, 2, so the rank is 2. That's it. So what does it mean for the original matrix? It means that what is rank? Rank, by definition, is the number of linear independent factors. And then now, what it tells you, the rank is 2. That means that you have only 2 linear independent factors here. Okay? So, part B. Determine whether this is linear independent or not. Okay? So the idea is that if they are linear independent, if they are linearly independent, then the matrix formed by these 3 factors, putting as rows, so this matrix 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, should have rank equals to 3. Right? Because if they're linear independent, then what is the rank? Rank is the number of linear independent rows, so you should have 3 of them. However, by part A, you have only 2. So this is a contradiction. So that means that they can't be linear independent. Okay? So the solution is very short. So the answer is no, because the rank equals to 2, which is strictly less than 3. Okay? By using A. According to A. Okay? And then part C. Part C asks you to determine the dimension of the span of these three factors. So the dimension of the span of these three factors, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, is so-called the row space, okay, row space of this matrix, because these three factors exactly come from the rows of this matrix. So that's why they're called rows. The span of this factor is called row space. And just now we know that from this theorem, we know that the dimension of the row space equals to the rank of the matrix. So this equals to the rank of the matrix, okay? And which we know by using A, these two. So done, that's it, okay? And also that makes sense because from what we learned in week 1, how do I determine the dimension? I look at how many linear independent factors are here. And then according to part A, number of linear independent factors here is 2, because the number of linear independent rows here is 2, okay? So this gives us a much more efficient way to determine whether a set of factors is linearly independent or not, without going through the painful definition. So study this example carefully, and because the calculation looks simple, but actually the logic behind it is very subtle. So please go through the logical argument very carefully, and if you have any question, please let me know.